Hi everyone, my name's Odom, and this last summer, myself as well as Trevor, Crupi, and Yonah Moise took part in an undergraduate research experience at ICERM. This is where we studied an iterative technique called multigrid, and more specifically, how multigrid can be used to more efficiently solve really large matrix systems that arise from Fourier Finite Element Methods on axisymmetric domains. So before we jump straight into our research, I'm going to pass things off to Trevor to give a little bit of background on finite element methods and how finite element methods give us these really large matrix systems. So here's Trevor.
So finite element methods are just a method of approximating solutions to differential equations. And what makes finite element methods unique is that they subdivide their domain into a mesh. And a mesh formally is just a set of subdivisions of a chosen domain omega in Rn into discrete geometric cells. And finite element methods use this mesh to approximate their solutions. So in order to get a better understanding of the finite element method and how the finite element method is using this mesh, we're going to look at a toy problem of the reaction diffusion equation over the unit square. So again, our two-dimensional domain for this problem is going to be the unit square, and we're going to divide our domain up using triangles. And going forward, if you hear me mention the idea of a mesh level, what I'm referring to is the number of triangles that we have in our mesh. So on the bottom left, you see a mesh level of 1, and as the mesh level is increasing, we see more and more triangles in our mesh. So next, I define the function spaces of interest. On the top, we have L2 of omega, which is just the space of square integrable functions. And on the bottom, we have the Sobolev space H1 of omega, which is the subset of all functions in L2 that have first derivatives in L2. And the big idea here is that a Sobolev space is infinite dimensional. And as applied mathematicians, we're very interested in the idea of convergence and how we can approximate solutions, especially using computers. And computers have a really, really difficult time grasping the concept of infinity. So what the finite element method does is it finds a finite dimensional subspace of H1 that we can use to approximate solutions of our solution to our partial differential equation over our mesh. So this finite dimensional space for our toy problem is going to be the space VH, which is what's called a polynomial space. So VH is the set of all functions VH such that when you restrict VH to a triangle, you get AX plus BY plus C. Now note that you can describe any vector or any function in the space VH by 3 coefficients, A, B, and C. This means that VH is a finite dimensional subspace, and because every element in VH is also in L2, and the first derivatives of VH are in L2, VH is a subset of our Sobolev space H1. So now we're going to look at the reaction diffusion equation. So our goal is going to be to find some U in H1 of omega that satisfies this equation. Negative Laplacian of U plus U equals some given function f, given Neumann boundary conditions. So the way we do this is we take the inner product on both sides of our equation with an arbitrary function v in H1. And as I mentioned, H1 is infinite dimensional, which is difficult to work with. So we're going to approximate this weak form by taking a UH and a VH in the polynomial space capital VH. And we're going to substitute that into this weak form and get the bottom equation. From there, we can rewrite UH as the sum of constants times basis functions in our polynomial space. And then on the right, we see that little VH, we just set equal to some arbitrary basis function because it could be any element in the Sobolev space H1. So we let it equal something that we know. And then we substitute these into our weak formulation on the bottom. And notice down here, we have J's and we have I's. So based on this, we can transform this into a matrix vector equation, AC equals B, where C corresponds to the coefficients of our UH. And then AIJ is the left-hand side integral, and BI is the right-hand side integral. And so now all we need to do is solve this for the C coefficients, put those C coefficients together, and we have our approximation. But there's kind of a problem. See this N down here, this corresponds to the mesh level that we're on. And if we have really, really fine meshes or we have really, really high mesh levels, these matrix systems can get really, really big. For a mesh level of 8, we can often have somewhere in the ballpark of 100,000 by 100,000 matrix systems. And classical methods like Gaussian elimination just won't do for something like that. So this is where we decided to apply an iterative technique called multigrid to solve this matrix system. Now, for this toy problem, multigrid has been proven to work on these simpler polynomial spaces like VH. But for our problem, we're working on much more complex domains. We're working on axisymmetric domains, which an axisymmetric domain is just some two-dimensional domain that has been rotated about an axis. So it has symmetry in about an axis. And so because we're often working with cylindrical type problems, it's much easier to take our problem from the Cartesian coordinates x, y, z into the cylindrical coordinates r, theta, z. So for our problem going forward, we're going to look at the canonical example, which is a unit square in 2 dimensions that we rotate about an axis to get a cylinder. Now, as I mentioned, we're going to be in cylindrical coordinates. And when we apply a Fourier decomposition to a vector-valued function u that exists on our axisymmetric domain, the symmetry of the Fourier decomposition actually allows us to drop the theta variable and perform a dimension reduction from r theta z to just r comma z. And then going forward, note that a specific value of k is going to be referred to as a kth order Fourier mode. So we're interested in electromagnetic problems. And oftentimes in electromagnetic problems, partial differential equations are written using the curl operator. So we're going to study a partial differential equation that uses the curl operator. And in our case, we're going to take the normal curl operator in cylindrical coordinates that you could find in a calculus textbook, and we're going to apply that to the Fourier decomposition from the last slide. And we get equation 2 down here. This is curl RZK of u. And this is our main differential operator of interest. So before, in the reaction diffusion problem, we were interested in the Sobolev space that was defined where the first partial derivatives were all in L2. But now, our new equation is going to use these curl operators. So our new Sobolev space, we're going to call H curl. And H curl is going to be the set of all functions u in L2, such that curl RZK of u is also in L2. So it's just the analog of the Sobolev space we saw earlier, but with this new differential operator. And then now we have to introduce a new finite element space ZHK. And this is going to be the analog of the polynomial space VH for our new, more complicated axisymmetric domains. I don't have time to go into the theoretical background of ZHK, but it has been proven to work for Fourier finite element methods on axisymmetric domains. And then we're going to call our basis capital X here. So this is going to be, equation 3 here is the weak form of our new problem defined on an axisymmetric domain with these curl operators. And we're going to use these Neumann boundary conditions that you see on the bottom. These are the analog of the Neumann boundary conditions for our axisymmetric domains. Notice that we are working in 2 dimensions, r and z, and we have this extra r because of the Jacobian transformation from x, y, z to r theta z, which is also why we include the r in the L2 up here and the r in our Sobolev space H up here. So just like before, we're going to do the exact same steps and end up with the following matrix problem. So this gives us a matrix system. And as I mentioned before, for really high mesh levels, this matrix system can get out of control. So our goal was to show numerically that we could use the multigrid method to actually solve this system a lot more efficiently. So the first question we needed to address is the non-triviality of multigrid when applying it to these axisymmetric domains. Because multigrid relies on subspace decomposition, even though multigrid has been proven for the subspace VH for the earlier problem, ZHK is much more complicated and it has a different subspace decomposition. So we cannot just apply multigrid to our new axisymmetric domains. We need to prove it mathematically. So next, I've just written out the Multigrid V-cycle algorithm, which unfortunately I don't have time to get into all of the steps here, but for anybody interested in applied math, I would totally recommend looking into it. So next, let's take a look at some of the results we got when we applied multigrid to the system of equations that came from the Fourier finite element methods. So first, we applied a different iterative method as a control called the multiplicative subspace correction method. Notice that as the mesh level increased, the number of iterations it takes to converge is increasing dramatically, going from 65 all the way up to 12,466. And as the mesh level increases, so does the convergence rate. Next, we see the multigrid results that we got for our Fourier finite element problem. Look at the dramatic difference between the MSC method and the multigrid method. I mean, as we go up to mesh level 6, we're only at 28 iterations to convergence compared to the MSC method's 12,466. And we saw that as the mesh level increased, the number of iterations to convergence actually stayed constant, as did the convergence rate, which means we know no matter what the mesh level is, what the number of iterations are, and what the convergence rate is going to be. Next, we compared them graphically. This is a logarithmic graph. The blue line here is the multiplicative subspace method, and on the bottom, we have the multigrid method. So it stays constant, and then the MSC method grows linearly in a logarithmic sense. And then next, we compared the convergence rate. Note that this is not a logarithmic graph, but the multigrid method stayed virtually constant, whereas the MSC method increased up to 1. Next, we decided to compare the convergence rate between various Fourier modes, and we found that as the Fourier modes increased, the convergence rate decreased slightly. So just some concluding remarks. The mathematical analysis of multigrid on H curl using our specific subspace decomposition has actually yet to be proven in a mathematical theoretical sense, but we are actually the first people to show numerically that the convergence is uniform with respect to mesh size. And then for future work, we're going to be extending our analysis to include the time harmonic Maxwell's equations and exploring some of the applications of doing that.
Thank you so much, Trevor. We just wanted to say a special thank you to ICERM for this wonderful experience, as well as our advisor, Dr. Minah O, and secondary advisor, Dr. Yunlai Chan, and our amazing teaching assistants, Justin Dong and Alex Mahai. We'd also like to say thank you to SUMS just for this wonderful experience and the opportunity to share what we learned with others, and hopefully this will inspire more research and more understanding of the field. Thank you all so much, and I hope you enjoyed.